So for those of you who weren't here, if I can do this in 30 seconds, the first lecture, we were trying to set the stage for all of this, and we went all the way back to a prehistoric man and looked at how we developed housing, what kind of housing it was. We developed communities, and at a certain point, and I sort of fixed it at the start of the agricultural revolution, that point enabled people to stay in one place instead of leading nomadic lives. All kinds of different things happened. One of them was that there was a split between the housing that the equivalent of you and I would have versus the housing that was used for people who started to acquire tremendous amounts of power. And then there were churches, and there were state buildings and banks and buildings of that nature. And then we moved into the extractive society, where we were, again, based on, with the Industrial Revolution, based on oil and coal, first coal and oil. And the numbers, if you look at this today, and I don't have charts, I flashed some charts on before that showed the use of coal, for example. It's been pretty constant all the way through from the 1700s. You know, we're using more as a proportion of how much energy we use per capita. It's been pretty constant all the way through. And now we're over 7 billion people on the planet, and we're still going to be using enough coal to provide 40% of all our energy. So we're actually increasing the amount of coal that we are using, and increasing, well, our use of everything, but particularly these extractive, what we extract, things that are not replaceable, not, quote, renewable. So I think, anything else to add to that, Ben, about
I think that's most of it.
The first couple of sessions? So, so we got knee-deep in the extractive society, and then we could see that there were alternate ways to be. And we'll be talking mostly about those alternate pathways in this presentation. There's an outline available. Those of you. All right, Ben, let her rip. This is somebody you all know and love, and it's a really fine portrait of him. I spent an hour today making sure that there were quotes that he actually used. It turns out that there's a forest of quotes attributed to Einstein that he never said. And there are about 10 quotes that are similarly worded from different sources, so that the authorities say he said things like this, but we couldn't find it exactly worded this way in print. But I took it to be that he had the wisdom to come up with this. And this is a situation we're in right now, because we're seeing from the top down, from the people who have the power to control how we do things, whatever sphere of life, the political sphere of life, the corporate sphere of life, they're much more comfortable staying with the status quo, because the status quo just is feeding them more and more power. So we're doing the same things. We have to realize, and this is my favorite analogy from the book Cradle to Cradle, we're in an automobile and we're going down the road at 100 miles an hour. Unfortunately, it turns out we're going the wrong way, right? So what do? Do you just grab the wheel and swerve in a 180-degree turn? Or we have to slow down before you can actually make the turn. Or the old folk wisdom is, the first thing you do when you realize you're digging yourself in a hole is stop digging, right, stop digging. We're still at the phase now, and you know, this happens, nothing happens evenly around the entire globe at the same time. But there are most places in the world, I would say, where we're still digging. We haven't stopped. This is what's going on. But we have to move in a different path next. We have to do things very differently. The world that we live in now is a result of old ways of thinking which are linear and fragmented. And we, according to our friend Mr. Einstein, we cannot use the same processes to extract ourselves from this situation as the processes that brought us to the point where we live. Next. All right? And we really have to do something else now. We're in a period of crisis. Many places in the world recognize that we have to do things differently and are way ahead of us. But it's time that we caught up. We have tremendous resources, both social and engineering in the history of this country. We have to apply all the skills and resources we have to this problem. Okay. And essentially, the first characteristic of doing things differently, curve number 3, is the old way. And this is time advancing from the left to the right, is to, instead of the old way where we have different specialties hooking in at their appropriate time, never talking to each other and never talking to the entity that's coordinating the whole event, whether it's designing and building a building or creating some kind of art event or a theater event, some kind of event. All the different specialists just work directly responsible to the coordinator and not have any discussion between themselves. And that happens, along this time curve. On number 4, not only do we push everybody's participation up to the front end, but we also encourage interaction between all the stakeholders or all the members involved in creating the event or the product, whatever it may be. Next. Right. So here we see, for example, just in site analysis, we're looking at all the different drivers, the different forces that impact a decision about what to do on a particular site. This is just a quick sample. Down here we can see we're looking at the sun and its path through the sky at different seasons and different times of day. That's very important for us to understand when we're doing a building. Here we're looking at what exists in our area, what are the resources, what are the features, right? The size of the site, all these the contours, the topography, that impacts drainage. That's what's being shown here from rain, which could cause erosion, which we looked at in previous lecture, and views. Then there are cultural decisions to be made about the project. So you want to bring everybody in on the front end and look at all these different aspects and get them laid out on the table, because somebody whom you think is just a plumber may have experience and bearing on the work of, let's say, the electrician or the duct person, or even may come up with a valid, wonderful idea about program. That has nothing to do with the mechanical systems of the building, but he just happened to have been to China or something and saw something that has bearing on the project, and he can convey it. We don't want to pigeonhole people. Next. So again, site analysis. Do you want to say anything at this point? You want to continue along here?
This is just a different way of diagramming some of the same things that were shown here: wind and climate and sun orientation. There's some of the symbols that you can see over there. So there's prevailing winds. There's existing vegetation.
Use your pointer.
Okay, well, it's just a different way of diagramming, but it's the way that we typically go about analyzing a site and integrate what the design possibilities might be from the beginning, taking into account everything, both the natural features and the built environment around it. This is one way of again, it's kind of showing it the design process in a linear fashion, but the purpose of showing this slide is that the whole thing really is a cycle, and the whole thing really should be a closed loop, where every aspect of the built environment, has repercussions in terms of cost at the beginning, and it has repercussions in terms of what it might be when that particular use is done. And all those things really should be thought about from the beginning, so that you don't end up with a 30-year-old building that the only real solution is to just throw it away.
This is something I'm always saying in the office, that user patterns trump engineering. We get very excited about designing and calculating things now, modeling and calculating, and we have tools and equipment, some of it very expensive and magical in what it can do, but we'll go out 3 decimal places and so forth. But with the best modeling and the best calculations and what your best imaginative projections are about how the building may be used, that gets all blown to hell when the users come into the building and do something entirely different that you hadn't anticipated. And then the building is seen as not working, the building is failing. This is one critically important reason why the user should be at that table at the very beginning, when we talked about how the process is different, how we're going to front end everybody, get everybody in the room together. It's not just the people who build the building who should be at that table. The most important people in the building, at that table, are the people who will use the building. They're the experts on what's to be done. If we design a building like this and we didn't involve somebody like Carol, who's in charge of program, how would we really know what's the right thing to do here? Carol is the expert on what programs happen in a facility of this nature and how they really work. So we'd be crazy not to invite her to the table and initiate the design process. Right. And here we have somebody, in spite of the engineer's best intentions, here's the thermostat, it's on a clock and everything else, the heat is on, and she's opening the window during the heating season. Or she's opening the window during the air conditioning season. Either way, it works. And this is these are simple things, but they have tremendous impact on how the building systems work. Especially if you went crazy and you sized everything just so they should be exactly the right size. Certainly not too small, but not too big. And that's very important with air conditioning, because what happens if you oversize the air conditioning in a building is it's satisfied by the temperature. The equipment is satisfied by the temperature first. That's how we have air conditioning, but we set the thermostat, not the humidistat, to control the on-off of the temperature. So the air temperature drops right away because we put in this oversized equipment, and the equipment turns off. And we never dehumidify. And the reason for having air conditioning is not to lower the temperature, but to dehumidify the air. It's the only way we know how to do that. Especially in our climate.
Right. We had a client who was not sure why. She thought there was something wrong with her mechanical systems, her air conditioning, because her electric bill, I believe, was $45,000 a year.
Yeah.
Yeah.
Right.
And we talked to her about it.
So why does she think something was wrong? Isn't yours something like $40,000?
Yeah, it wasn't. We came on board. She'd been living in this house for a while. We had nothing to do with the early stages, and we didn't stay on that project very long anyway. But we walked through the house with her to see, what it might be, what she's doing, and she says, "Oh yeah. Well, first of all, the thermostat was set for 64, I believe, 64 degrees. Yeah. And then the April air system, which is a humidification system, was set for 75% humidity or something like that.
High, yeah, 60.
So just there, the air conditioning's running and the humidification systems are running at the same time, fighting one another. And then they'll go and open up their giant, you know, nano wall door at the same time, right near the ocean. So you're getting, I mean, it was just, she didn't want to admit that it was a problem with the way they were using the house. She thought it was, you know, the mechanical systems are wrong or they're not running properly or whatever else. So
Yeah.
people, it's true that you can design, even if it had been designed well, which we're not sure if it was, it's just a matter of even sometimes setting up the controls properly so that someone can adjust them themselves, but more importantly, adjust it to the way they typically live.
Just to finish the air conditioning, if you oversize and then you're not dehumidifying, then you get cold, clammy. And cold, clammy is not only uncomfortable for us organisms, but it turns out to be really terrific for mold and mildew. So all of these things can go haywire, and we're doing our job right, so we think, but again, user patterns trump engineering. Next. Okay. So we talked earlier about how the built environment interfaces with the unbuilt environment, or the so-called natural environment, but I'm really fixated on how the built environment is the armature for the social landscape. And I was looking for some examples, and I think this is one you all know. This is the mall in Washington, D.C., which is lined with all these different museums, right? These are not buildings that have to do with how government functions. These are buildings that have to do with who we are as citizens of this country. And there's a map there before. We can read these out if you'd like, but it makes the point, right? Okay. And then another similar institution with a space designed for what it needs to do socially, right, culturally, right? I'm not identifying this, I assume you know what these places are. However, I'll tell you, this is Amsterdam, and on a smaller scale, on a little commercial scale, it's still important to be able to meet and bond with your fellow citizens, with the other people in your community, in your neighborhood. This is something that's really lacking in the settlement pattern that we have out here. It's horrendous. So it's the first time I bumped into Tyler in I don't know how long, almost a year maybe, and yet we operate in similar worlds and we're at parallel interests, and because we don't work around in the same building, as it turns out, you know, we don't bump into each other, where if we lived and worked in a community like this, we'd have coffee at least once a week, I'm sure. Right. So that's Amsterdam, Copenhagen, the same thing. And of course, we couldn't show slides like this without stopping for a minute in Gay Paris. Right. And interesting enough, just go back, interestingly enough to me, everybody's blocking the sidewalk. This is all tables and chairs, right? So if you're a pedestrian, where are you going here? There are no cars in this street. This the pedestrians go here, and this is all for. And we saw some, I saw in particularly Avignon and in Arles, I saw double-tiered sidewalks, you know, curbs, double curbs, one curb that delineated the dining, and the next drop down. This was pedestrians, and then a drop down again, another curb for vehicles. And in Berlin, I saw a double curb at the road edge, so there was a slow vehicle lane. Now we call it slow vehicle, but a bicycle lane, and then the car parking and the cars driving. So there are ways to do this. Now, it seems terrific, but when we take another layer of issues and overlay that, the issues of handicap accessibility and adaptability, this could be problematic. Although since we've enacted the ADA, and we just had the 25th anniversary of the ADA, Americans with Disability Act, virtually all the curb cuts at the corners of of traffic intersections virtually over through the entire country have been brought into conformity. So that it can be done. It can be done. Next. This is for you, Ben.
Okay. This is really talking about how we measure some of these things that we're talking about. What are the metrics for establishing what is green design, what is sustainable design? There are different ways of doing it. The USGBC, which is the United States Green Building Council, which is actually a private company. It sounds like a government organization, but it's not. Were some of the first really to come up with a universally recognized and used system, which is the LEED system, which is Leadership in Environmental Energy and Design. Thank you. So they have certain standards which they're updating all the time. They've changed it quite a bit. It used to be basically one standard for all building types, and it's become quite complex actually. There's at least 8 different genres of building type, and then within that, you're not just someone that's taken the test and is a LEED professional who can oversee the process. There are different divisions within that, so it's become very specialized. A lot of it, I think, actually has to do with the business of operating this system, but nonetheless, it's a pretty good system for measuring how sustainable a building might be. They use some of the major categories: location and transportation, sustainable sites, water efficiency, energy and atmosphere, materials and resources, indoor environmental quality, and then innovation and regional priority. And you get so many points. You don't make it up. There's pretty strict guidelines for these things. So let's say, for example, and again, starting at the beginning of the process, with the site selection even, if your site is within such a distance, I forget what the radius is now, but again, you're given incentives to be accessible to public transportation that is already existing, obviously. But if you create a new public transportation stop at your building, you're still given points, but probably not as many as using the existing. That sort of thing, allowing for bicycles and shower facilities in a building so that you're encouraging your employees to not use their car. These things for site, you get into issues of water efficiency, and again, you're given a score in these different categories, and when it's all totaled up, you're allowed to give yourself, you can see what the range for points is. So you're either LEED certified, which is the lowest standard, but it still requires 40 to 49 points, and then the next level is silver, and then there's gold, and then there's platinum, which is the highest echelon. There are tax incentives to help you with all this, to incentivize the process in the first place. But we, in our own office, actually don't do this personally. It's difficult somewhat. It's definitely what's the word?
Well, it's expensive for our clients.
Well, yeah, there is a cost for it. They're having to go through the process itself, and they're having to change the design sometimes to accommodate things which they wouldn't necessarily otherwise. So there's a cost to it. There's a rigor to it that is definitely time consuming. So we like to use this as a guideline, but we don't necessarily encourage clients to become LEED. But it's certainly a great guideline to use. There are other ones This is the Green Globes checklist, which is similar sort of categories: site, energy, water, resources, building materials, etc. I don't know how the scoring works for this, if it's the same.
This is from the National Home Builders use this system. And the main difference between the two is certification for each step. With LEED, they do an independent third-party certification of every little point. So you have to get somebody else in, and sometimes this costs money too and takes time. Some other expert comes in and they see that you've done this, you've done it the way we expect to see it done, and therefore they issue a letter with this signature saying that this point complies with the rating system. And that happens through the whole checklist if you're LEED. You can self-certify to a large degree in this with the National Home Builders list.
But I don't think the tax incentives and the other incentives that you might get from LEED, I think, are more substantial and therefore require third-party verification.
Not necessarily. Yeah, particularly from government, because they don't want to be accused of a monopoly. Right. These are considered professional engineering compliant standards, whether they're certified or not, and you're eligible for whatever programs the governments have that involve money under any one of these banners. Okay. Right. And this is...
It's the Energy Star checklist, which is something that a HERS rater now in Southampton Town is mandatory. Mm-hmm. This is the homes version, so you can see they're going through, well, this is just part of the checklist. Then they're actually taking the energy modeling information from the plans that we would provide them. So they are taking the U value of all the windows and the walls and calculating what the building should perform as a number, as a metric. And then they're also integrating this whole checklist at the same time, which talks about, actually, I guess this happens during the walkthrough. This is not so much.
And before, and when you file the plans.
Right. But some of this actually has to be observed, you know, not just that it's on the plans, but that it was actually built that way. So they're checking that all the ceiling was done, for example, where the frame wall meets the foundation wall, that's all caulked, and that all the air infiltration is minimized. They're looking that the ductwork is all sealed properly internally, as well as if it's in an unconditioned space, which is not a good thing. But they're doing a blower door test to reinforce that. So not only are you checking that you're sealed everywhere, but then they take this, I don't know if anyone has seen this, it's a big fan basically attached to a piece of fabric, and they open up your front door and fasten it in there with a frame and make it relatively airtight, and then they pressurize your house and see how much air you are actually leaking. Right. So that has to be done, and it's actually part of the Southampton Town code now. Blower door test is only for mandatory commercial buildings.
Yes, but it's mandatory. It will be mandatory with the new code, the New York State code, coming early 2016, right around the corner. I want to take a minute and just say, you know, I've been doing this for quite a bit of time, and when I started, there were no metrics. We were just the good guys. We were the guys on the white horse, you know, we were the knights in shining armor who were doing the right thing. And we were doing all the weird things too. We were doing the earth-covered buildings, you know, we were doing the straw bale buildings. We were pulling out every other technology we could think of. And we were having a lot of fun, but we honestly believed that what we did was in the interest of at least lowering energy usage by the building. But nobody really knew. We knew how to, you know, I'm talking about the architectural design community, not the engineering community. The engineering community had always modeled their buildings and figured out what the loads were, particularly in commercial applications. But in residential applications, this was not happening. So what we've realized, what U.S. Green Building Council did, the very first step was the concept of bringing metrics to this whole market, and that we now, quote, build by science, not by folklore. It's a huge shift. The other saying you may be familiar with, you know, you measure what you care about. And it's easy to put numbers on certain aspects of the building that you can quantify with some kind of device, a ruler or a pitcher or whatever it is. But we're interested as well is the things that are not easily measured with devices. In other words, some kind of qualitative measures. You know, what is this room like? Could this be better? And in its different aspects, we can measure its acoustic performance. We can measure, you know, how durable the flooring is. We can measure other aspects, as Ben said, the U values, the resistance of the glass to conducting heat through or not. We can measure those things, but when it's all said and done, the experience, you know, is sort of an art. You don't think about the spaces as you move through them, or the built landscape, or the natural landscape. You don't think about those in terms of numbers. You think about them in different ways. But we still try and quantify the qualities wherever we can, so that we can see that we're progressively making better buildings, better now being defined. Okay. So we finished the metric issue. A brief recap, we showed you this building last time. It's the Frank Lloyd Wright second Jacobs House, which was done, I believe, in 1939. And this is his solar hemicycle. It was also earth bermed. The north side, thank you, north side has earth all around it on the first floor. And you enter through this tunnel, the entry tunnel. You come into the south courtyard, and the sun, it's not a straight building the way we're used to seeing them. It has this arc, so the sun rising in the morning is hitting this part of the building, not here, it's going here. And as the sun comes around during the day, you know, from the west side, before the sun sets, it's coming in the east end of the building. A really amazing building, and a lot of work was done by Frank Lloyd Wright at this time, and by the Keck brothers, also in the upper Midwest. The overhangs are designed to shield the summer sun, which is at a high angle, and allow the winter sun to come fully in. Even this balcony of the second floor is cut back to allow for that and allow for air circulation. This second floor, incidentally, is suspended from the roof with steel rods every so often. It's a great building, and was done for very, very little money. Radiant floor. Frank Lloyd Wright brought us the hydronic radiant floor. We know in traditional folklore, there were, particularly in Korea and China and Japan, there were air floors where the flue gases from fires were led under the floor, and the Romans used that as well to heat their buildings. But Wright put that in piping, and there was a big renaissance of radiant floors, and certainly right after World War II, Levittown used radiant floors here on Long Island. Next. Right. Just another Usonia house. Frank Lloyd Wright, with this line of building, the Jacobs House was the first one, but developed a series of buildings that used very much the same detailing and technology and materials, just concrete and wood frame, and but he organized the plans in such a way that these were the first true middle-class buildings, not like a Victorian buildings that we know and love and we see. There's some right on Main Street right here in Bridgehampton. They were designed to be operated by staff. There was a butler's pantry. There were maids' quarters in the attic and so forth and so on. Here, this is operated by the user. So the kitchen is open to the dining room. The whole space flows. This is the living room and the dining area, and then down a little corridor, in this case only 2 bedrooms. He also gave us, invented the carport, and there's a dramatic photo showing that the overhang of the cantilever of the carport is just really fantastic. Occasionally brick pylons. He would sometimes switch off stone for the brick. But these buildings were simple and inexpensive. The first Jacobs house was done for $5,000 back in 1936. The journalist's house. This is the interior of this Gertz-Winkler house. Okay. And now we come to Arup Associates. We want to show you a bunch of their buildings. They first came on the scene as just architectural engineers, and they did the structural engineering for this extraordinary complex building by Utzon in Sydney. It's the Opera House. But they were interested in the beginning too in environmental design, and actually had architects in-house and provided integrated design with full architectural and engineering services, including all the mechanicals and electronics and plumbing and so forth. And that's what they're really known for. They're headquartered in London, but they have offices in New York and in cities all around the world. They do amazing buildings, which you will see. You can jump in any time. This is just, I think, a decorative greenhouse at the Bacardi Bombay distillery. And this is the Mushroom House. Take a good look at it, and then the next slide has some text that's descriptive of what it's made out of and how it works, all right? So I won't read it to you. I assume you can read it. All right. So they're working, very hard to close the loops here. And their carbon footprint is Z.
When was that built?
I don't know. I'm sorry, I don't know.
What's the reason for it?
Well, this was an experimental structure. This is the Mushroom Tower, but it's just showing the feasibility of the material. It's a test to build so I don't know when this was built, but if it looks like it might have some years on it, I would guess it's at least 10 years old. And the question is, what condition are these bricks in today after 10 years standing outside? Oh, okay. And another structure, very imaginative structure in Spain in a plaza. I don't know exactly what this does other than create some kind of shelter and modulate and define the space a little bit, but or what it's exactly made of. I believe it's steel, painted steel, but it could be something else. It provides shade, which they sorely need in Spain. And this is a vertical farm. They call it Sky Farm. And the nutrients, are applied at the top. I think they're pumped up and then trickle down and distributed vertically so that we're not taking up so much of the landscape. I learned the other day that there are farms now that are indoors that use 5% of the energy of traditional outdoor agriculture and take up 5%, 2 to 5% of the space. So we are over 7 billion people on the planet. We currently use all the land that we have on the planet. Approximately half is used for food production. And we have, by all projections, about another 2 billion people on their way here by 2050. And hopefully we'll level off then. We don't really know. We'll have to stick around and see. But food production and resource use by the whole food agricultural sector is an enormous issue. And how we respond to that, what are we going to do? It was a suggestion by at least some people who are working on this that we should be growing this stuff indoors. So there's another building type, not barns anymore, but other kinds of agricultural buildings that will actually, via grow lights, produce our food and do so very, very efficiently.
That building is lit by the sun energy is still used to, are the grow lights?
Not for this. This is not a grow light building. No, I'm talking about buildings that are totally indoors that'll be used with shelves, racks of trays of plant medium and being used that way, almost like a library. You walk down corridors and there are racks of, If you go to Page Restaurant in Sag Harbor, they have a vertical wall in the back, and they are growing the greens for your salad right there at the restaurant, and they have a couple of grow lights and some trays in their basement where they're also growing other greens for your table right there. So this is happening right in our own neighborhood. This is an extraordinary building. This is a solar chimney. It's a project. I think that
This is a design.
unbuilt, right? It's just a project. I believe they did build a section, a little sector, part of this in North Africa. It's designed to be built in desert country where not much else is happening. It's huge. I don't know what the diameter is, 1/2 mile or something like that. This blue line here represents a greenhouse roof. That big disc in the previous slide that's around the central chimney is a greenhouse roof. And the warm and the air from the desert is drawn in from the perimeter because of the stack effect. It's heated by the sun. So as it heats, it's going to go out and up and create a fantastic draft. This is the mega super chimney. And that draft will be used to drive turbines. So this is a way of producing electricity without all the reflectors and the other things we see, just a different form of wind energy, but combined with solar here. And I found the interesting part about this design is explained over here. You are taking in solar energy through the glass, and we know that greenhouses work because they are relatively translucent to light energy, but relatively opaque to heat energy. That's short, they're relatively translucent to short wave forms of energy and relatively opaque to long wave forms of energy. That's why we have glass doors and windows and greenhouses. That's the principle on which it works. So this big greenhouse, this giant circular greenhouse, is heating up the soil. So at night, when the sun stops shining, it radiates its heat out also, and continues to heat the air, and the chimney continues to work even at night, which means we're getting power, at night. This is all from Arabs. And a new bridge proposal for the Thames. This is also a testament to what we can do with our new computer renderings, the tools that we have to work with. Unbuilt, but I don't doubt that sometime this will come. But a concern with restoring, regenerating nature and reintegrating the natural environment into the built environment. This is why Carol had us come and speak with you here in the Natural History Museum, that the new green buildings are literally green, that we're sensitive. The design and engineering community responsible for them is very sensitive toward looking at the issue of integrating the built landscape with the natural landscape. This, at first glance, looks like a solar collector, one of those, you know, it's concentrating the rays of the sun, obviously, on the top of this tower, and then there's a boiler up in the tower, and it runs a generator and creates electricity. But look again, and you'll see that this is just one side of a building. So this is an integrated structure. I don't know if it supplies power just for itself, and there must be some kind of thermal storage, or it's just a community and regional power electric generator. But the structure, the money that you'd spend to build the skeleton structure for this is put to good use by also becoming a building. Right. So if you're going to do a building, we want you to know that the first things you'll check out are the features of your site. And there are a whole raft of those different features, and I just illustrated some of them with these graphs and diagrams. So this is a map of the United States showing where you're likely to find good geothermal, natural hot springs, you know, like Iceland. Iceland runs its entire, the city of Reykjavik on thermal geysers from below, right? Gordian's been there. And wind power, depending on where you are. If you look at these maps, you'll see that Long Island is really favored with a lot of these natural resources. We have very good wind power. It's an average mile. I remember it being over 13 miles an hour. And that's in agreement with our chart here, out on the east end. And 13 miles an hour doesn't sound like very much for an average annual flow, but it's average, and it's for the whole year, all the time. So there are many times where it's blowing much more than that, many times where it's not, but average over the year, 13 miles an hour is a very significant amount of wind resource. Next. And insolation. Long Island, we have the same amount of insolation as Nashville, Tennessee. Wind roses showing what time of the year, what season, which direction the wind is blowing, and with what intensity as an average, you know, depending on your location. So these are done with sensors that you erect on your property to figure this out for whatever, a whole year cycle. And this is a funny diagram, but I thought it was important that also by location, depending on what state you live in, your codes, your energy code is different, right? And it also happens to show the evolution of the codes over time, this being the average existing home, how much energy it would use, and establishing a little better, taking a 2006 international code baseline here, a little better performance. We can see that now, from 2006 to 2015, the New York State Code, which is now adopted but will go into effect in 2016, is based on this. Half the amount of energy, less than half the amount of energy the average existing home used in the year 2000 even, not so long ago. Excuse me?
Average American home?
Average American home, right.
And there's still some states, you can see up here, that don't have an energy code, or that haven't adopted one.
No state
and
code
don't
here.
mandate it.
Right. And there are parts of New York State where you don't need to comply with a code where the towns, the way it works is there is a code, in most cases it's a state code. The state writes it or they adopt a code, and now we're getting together so that state adopts the international code. If your town does not adopt that code, then there is no building code where you live. But as far as I know, there's no place in New York State where you can build without getting a septic permit. And that's usually issued by a county government. Okay. And this is why we're speaking with you, is because the design and building community is responsible for the largest single sector of energy use in this country, almost 40%. And we can see how it splits out versus residential versus commercial. And again, the biggest users are what you might imagine. It's heating, space conditioning, cooling, and lighting and water heating. And this number is rapidly going down because of, anybody? Right, LEDs. We have a little story about that coming up in a minute. And here you can see the electrical generation. On this side, it's how it's generated and then how it's used. Right? And this is our use in 2013, 97.4 quads. And I'm going to put my friend Gordian on the spot and ask him to define a quad for us. Oh, okay, all right.
Wait, I think it's...
We'll have to look it up.
No, it's not. It's a lot of energy.
It's a lot of zeros behind, right? Just a lot of zeros behind it. Okay. And this is a very interesting chart in that it shows, again, measure what you know. That when we start to measure, we were learning about the buildings, that they were doing things that we hadn't realized. That these are all the different technologies for attempting to save energy use in a building. We'll read out a few. Staggered studs, a double stud wall, or a single stud wall with the studs staggered. So half the studs are carrying the inside finish, the sheetrock, and half the studs are carrying the outside finish, the structure. My favorite, structural insulated panels are here. Double walls, insulated concrete forms, which are those big foam blocks, and they pour concrete in the middle. Straw bale is here. But the single biggest impact on energy savings is the size of the house. Here's a house, they say large. They haven't been out here. They don't know what large is. 3,424 square feet. That's the largest user on the chart. The bottom of the chart, green certified extra small home, 1,149 square feet. And it looks to me like it's using 1/20th of the energy of the larger home, even though it's 1/3 the size. 1/3 the square footage, 1/20th the amount of energy. Okay, and this is your story.
So this is just an example of how the whole process is really important and why integrated design is so important. So, for example, these are paint chips, which I think most of you are familiar with, and if you look on the back of them, there's a little bit more technical information usually. That's usually the manufacturer's color number, but it's also the reflectivity of the color itself, so how much light energy it's reflecting. So it used to be that a lighting designer, let's say in a commercial building, and you get into a large building, there would be a lighting designer that would be working independently from probably the interior designer who would be picking the colors. And if they're not communicating, the interior designer might pick a darker color that they think works with the rest of the space, but the lighting designer working in their little separate bubble has no knowledge of that and has designed the lighting based on a standard white ceiling reflective paint, and they're going to end up with a building that it's always kind of dim in here because the lights were designed, the layout of the lights and the wattage of the bulbs and their spacing and everything was designed based on so much percentage of it reflecting off the ceiling and therefore lighting the space.
And what if they do talk to each other?
Well, if they do talk to each other, well, things have changed a lot too, just in terms of LEDs and the ability to, actually now you can not only dim lights and increase the output or decrease the output on the fly, but there are LEDs now where you can actually change the color on the fly as well. But if they are talking to each other, you'll end up with a building, you know, a space where it's not dim all the time and just not quite bright enough, or too bright because they picked the really, really brightest white ceiling paint that they could possibly pick, where you end up with a harsh space.
Well, you increase, if they pick a dark color, and the decorator says to the lighting engineer, oh, I'm picking a light reflectance of only 30,
right.
You know? So the lighting engineer increases all of the amount of light, increases the wattage, the amount of electricity uses, and in the old days before LEDs, that increases the heat in the space, which then he has to call up the HVAC engineer and increase the size of the air conditioner.
Right.
Just because the decorator picks a certain color paint. You know, we say, in the design world, they say, we want well-integrated buildings, or we practice integrated designs. This is the key to the future. Well, the truth is, all buildings are integrated. Most of them are integrated very poorly, but they all work. You know, if you push a button here, something else happens there in the building, just the way that's true about us as organisms. So we're looking to make sure that they're well integrated and that all these little effects between one system and another are accounted for and understood. So when we design and set the whole thing up and have the controls running accordingly, it works the way we want it to.
Right.
Okay.
I mean, it's a scale thing as well. I mean, this is typically, it's a large commercial building, it's an office building where the heat loads are not necessarily from what's going on outside, but usually from the heat that's just generated inside the building. So they'll be running their air conditioning sometimes in the middle of winter because of plug loads, you know, computers and people and lights generating so much heat that they're having to run the air conditioning in the wintertime.
Yeah, particularly very common, run the air conditioning on the south side of the building and running the heating on the north side of the building, instead of pumping the heat from the south side to the north using much less energy. That's the old way. All right. This is another example of integrated design. You want to?
Go ahead.
Okay. So we had, this was part of a whole house that we inherited the design from someone. And in this area right here was a two-car garage with a column in the middle. And this got turned into a family room, so the column had to go away. So we had to restructure the roof, which turned out to be the upper floor. And on top of that floor were two bedrooms, two girls' bedrooms. So we had to re-engineer the structure. So we put two beams at third points right here. And I don't know if you can see it clearly, but we echoed those with, pardon the word, fake beams here and here at third point. So we had a coffered ceiling of 9 panels, which would look very nice. This was on a slab, the garage. So we had no way to get the ductwork up to that second floor bedroom. So we brought the ductwork up here in the wall between the garage and the building, and the ductwork became, these steel beams became, instead of wide flange beams, the H-beam that we all know, here's the beam. It's a steel tube. We sized the steel tube to be the right size for engineering the loads for the structure, and we sized it also to be the right size for the duct. So one of these steel beams was the supply. It says supply structural tubing duct. That was here. And the other one was the return, and we had to put holes in them, and they connected. They picked up these little feeders and the registers. This shows the layout. And this was the duct system, and it was the structural system. And these fake beams, which were made out of those cast foam, you know, unless you got within 3 inches of them, they looked like old weathered barn beams, big old beams, but they're made out of foam, polyurethane foam, right? Instead of making them big solid chunks of foam, they hollowed them out. You're really buying a 3-sided piece of foam, a U-shaped foam. That, we looked up the size of those, and it fit exactly around the steel beam. So that became the insulation for the duct as well. So on all those 3 levels, because we're doing this in-house, since we engineered and sized the ductwork, we engineered and sized the steel, we could do this integrated design. Next. And then we picked up some eye candy for you. Let's see, just wind up with some of these. These are buildings around the world. I don't even know who the designer is, but this is in New Zealand. It's on a steel tower. This is the HVAC system for that building. It has, let's go back, I think you can see, these are the electric solar collectors, the photovoltaic collectors on these ribs here. So it has photovoltaics, and it has a heat pump and so forth, and this outstanding view. There are other slides, other views, but just to quickly show. And this is where Carol is going to move into her new building. This is the Natural History Museum in Shanghai, recently completed with a living wall. This is not painted green, that's all plant. That's all plant material. And then we have some slides about co-housing, because again, I'm very interested in the social impact of our buildings. And co-housing originated in Denmark over 35 years ago, and it's really, if you think of a dormitory, if any of you actually had the experience, you went into a dormitory which was, it had a big living room and a kitchenette that everybody shared, but you all had your own room. So if you blow that up to be a community, you have a smaller house, you have a very small private house. It has a kitchen, it has bedrooms, but it's smaller. And then there's a common house, and the common house has community dining, and it may have a whole bunch of other features. The money that you save by not having a big house with all kinds of stuff in it that you would have usually, that we have out here now, goes into the community house, and you can have collectively, you can collectively have a share, or the collective owns, you know, a wood shop. Used to be a darkroom was a favorite. We don't do that anymore. But other, you know, other things that are just extravagant for some person to own on their own, but together you can own it, even the automobiles. And that's how that works. The laundry, instead of everybody having a laundry machine, a washer and a dryer in your house, how many hours a month do you think do those run? Hardly ever, and every house has them out here. It's crazy, right? So here that would happen in the common house. Next. And common characteristics, they talk about governance, and that it's intentional neighborhood design, and that everybody shares collectively in the decision making. And in the very beginning stages, meeting with the architect. Again, the user is the expert, and telling the designer, this is what we want, this is how it'll be, and help us to make this happen. So a couple of examples of just plans. And this is in Maine. And they have a huge site, and they've saved, quote, saved all of this. This is turned into a recreational natural landscape, all of this. There are some fields over here, and I know that there's some gardening and planting. There's a goat shed. This is the septic leach field. So they saved, quote, saved all of this, but use it recreationally, and grouped themselves together. There's a common green for outdoor common space, a soccer field, some playing field, and one of these is the common building. It's not labeled. 2 common buildings?
Probably.
Maybe, okay. Here's same idea in Utah. Actually, Ben, I think this is not done so well. They have a relatively large site, but they've sort of gobbled it up with the same kind of site spacing that you would have in a conventional subdivision. And so there's a treat area, but there's no real differentiation or setup for how to use the site. And then the infrastructure, the parking and the pedestrian park gets spread apart and costs a lot more. There is a common building, but it's really not it's not taking full advantage of the concept. Next. This is much better. This is in Washington State, and I imagine in a more urban setting, maybe not in the village, but on the outskirts of a village, where every square inch has to be accounted for. But so it's very efficient, and there is, again, this was an existing house. This might have been this existing lot belonged to this existing house, and then they added on a big common room, and this became a co-housing project. And finally, in Mountain View, California, everything happens first and best in California, right? We have a row housing, you know, as compact as we can get, and leaving as much as a landscape as was possible. This is more of an urban situation. So you can have co-housing in all different formats, in all different regions, in all different zoning situations. Next. And I think this is our last, we're trying to wind up. This is BedZ in Beddington, a suburb of London. And there are 82 units here of live in and work at home, live at home, retire at home, stay at home houses. And they have these glorious wind vents that are very, very expressive, right? That mark the community, and you can see lots of glass. You can tell which is south, right? We're looking at the south elevation of all these buildings. Very successful community. Next. And diagrams of how the different systems work. They also have wastewater reuse, you know, gray water recycling. Again, classic passive solar. Watching that the overhangs are calculated for shielding the summer sun and emitting the winter sun. And some of the stats, I think, I don't know if they're on this, yeah. 81% reduction in energy use for heating, 45% reduction in electrical use. These are compared to local averages. 64% reduction in car mileage, 58% reduction in water use, 86% of the residents buy organic food. And I don't know, the other 14, I guess people don't even talk to them. I'm not sure how that works. And in the community, residents know 20 neighbors by name on average. So again, a metric, how do you measure community? And they picked out this metric, how many names do you know of your neighbors? But there are different ways of measuring. It's fueled by a biofuel. This is combined heat and power. So this is essentially a diesel which runs on biofuel, not diesel gasoline. And the heat that all these combustion engines produce is used for either hot water heating or space heating. Right? So PV, of course, rainwater collection. So there you go. Next. And a slide showing all those systems and the end elevation. It's just a lot of fun. This is sort of like the banjo of the orchestra. You know, you can't play sad music on a banjo. You know, you have to sound, this housing, nobody is unhappy in here. I just can't picture how that would be.
Well, the 14% not buying.
Oh, the 14%, that's right. 14% are unhappy. Good question. Well, I'm trying to work on a co-housing project in Sag Harbor. I had Robbie Stein's ear, but Robbie Stein didn't make the cut for, you know, but he's, you know, so we'll see. But I'm going to make an appointment with the newly elected mayor of Sag Harbor, see what I can do with that. But all these other fronts, we talked very briefly about this at the end of the last session, Tyler. Everybody has some particular interest or something that they have your own button, whatever it is that gets you going. There's got to be a way to channel that to make any part of this happen. whatever that may be. You know, for Ben and myself, this is what we do, and this is what we really enjoy, but if it's just organizing with people and just getting the word out, some of you are really good communicators or you're involved with media, that's very helpful. And we know that in this community, people do turn out to try and make things happen, and to register their feelings about things. I had been away from East Hampton for many years. I couldn't be there, and when I came back on the first night, there was a demonstration at the windmill and the square for the doctor who was shot by the anti-abortionist, and this was a memorial ceremony, a candlelight ceremony, for the black man who had been dragged behind a pickup truck in Texas, and the gay teenager who had been hung on a fence and tortured by people, you know, and the community of East Hampton came together and had an event, a candlelight celebration to mark these events. There were 150 people there. So there are all kinds of things that can be done. And if you want to call us at any time in the office and talk about these things, we'd be happy to do it. But I suggest you look inside and find the thing for you that you're interested in. There are a whole bunch of different angles. We showed you all different aspects of this world, the industry. You can approach it from the natural sector. You can hook up with Carol and find out what can we do about improving the landscaped environment or the natural environment, the recreational environment, the what's the word I'm looking for, where there's just where wild, a forever wild environment. There are sectors of that too. So talk to your elected officials. Say that these certain things are important to you. They have to know that. Yes, we're trying to promote, right, all future development in the villages and the hamlets and not in the space between. And I mentioned this at the last lecture. Every time I get, and thank you for bringing it up, it's another opportunity for me to mention it, I don't like the phrase open space. You think, how could that be, Bill? You're for open space. No. Open space means we don't know what's going on there. And it also means we don't take responsibility for what's going on there. It's undifferentiated, it has no functionality, and we don't care. That's open space. I prefer the managed landscape so that it has specific uses that we need to make our lives richer and healthier. Whether it's clearly, you know, growing food is one, but recreational uses, restorative uses, sustaining all the flora and fauna. The diversity is important for the health of the system. So there are many specific uses that the space in between the built environment has important uses, and they should be called out and documented and maintained. So we call that the managed landscape. So yes, these are all fronts we can be working on. Well, we really, I mean, you can talk about let's change the economic and marketing system, you know, or the zoning system. I don't really know. We do have, for example, it's kind of funny, it doesn't come into play on the high end, but on the low end, there are, when we talk about workforce housing or affordable housing, the housing that we provide for people there, that's in perpetuity. It's not a speculative market. A person who is working their way up the ladder, and they go in there and they buy an affordable house because it's all they can get, and they're lucky to get it. If his salary doubles or triples or goes up 30%, or when he prices himself out of the house, he has to leave the house, but he can't sell it for market value. He's got to leave it at a price where it stays in perpetuity as accessible for affordable people. So we've looked at developing a mechanism on that end. On the other end, I don't know, if you're a wealthy person, we get this. People, they call designers and engineers in to restructure it, reshape it, so it matches their needs better, whatever they may be. We do call it repurposing, and that in a way is a way of recycling the building. We looked, it was last time, I think we had Mies van der Rohe. The first session we had Mies van der Rohe's building up. Mies van der Rohe created what he thought were universal buildings. It was so flexible, you could repurpose them very inexpensively for all kinds of different functions. So we might take a page from his notebook, and this is talking about this. This is a concept that was in the 40s and the 50s that is 70 years old now, where we could go back to that idea. And when we build office buildings or commercial buildings, that they would be more universal. If you go into the big cities and you go into the buildings that were there before World War I, the big warehouses, the loft buildings, they were universal buildings. All kinds of things went on there. So out here, people make a signature building. It has a specific sculptural shape. It's very hard to change and to use for anything else.
Architectural firm look for?
Yeah, right. What constitutes a good architect, right?
And how do they know?
How do they know? Right. Well, one of my pet peeves is you can graduate high school, or let me turn it the other way around. You cannot graduate high school without the name William Shakespeare meaning something to you. You cannot graduate high school with what?
We hope.
Yes, we hope, right. William Shakespeare. But you also probably will know the name Beethoven. You will also know Walt Whitman. You will know Albert Einstein. You will know, certainly STEM, the science, math, and technology names. But culturally, there are certain, in most fields, you will know the names. There are certain people know contemporary composers, but you can easily graduate high school without knowing anything about architecture. So I would love to see more programs. For the same bargain rate as we charge for this series, we're available for others. We'll go into the schools, and I always have, and as have you, go around. So we need to do this. We need to educate. Everything starts from there. But in terms of studying, how to hire, what is a good architect for you, you have to delve in. Roll up your sleeves and get into some of the literature and have that kind of feeling about it, because mostly we're lazy, and we're in a society where people want to do the right thing. Again, they want to spend the money on the right thing. So they'll say, I want a greenhouse. And we hear this all the time. Well, what is a greenhouse? Well, it's got a heat pump, and it's got a bamboo flooring, and it's got photovoltaics on it. Those are the three defining characteristics. When actually, what I hope we learned here is that that's farthest from what we're concerned about. That's really the least of it. So somehow we've got to get this word out, that it really starts with local materials. It starts with a thorough understanding of what the needs are, and it's an integrated approach, keeping your eye on energy and local materials.
You can call for a home energy audit, and they will come in much the way I was describing the blower door test and other things like this. So they will measure where your house is right now, what problem areas there are, and how you might address them, and what you can do to improve them. They won't do the work to do the improvements, but they will point out where your deficiencies lie, and they will, I think, put you in touch at least with resources for you to work at that. But yeah, right now,
And it doesn't cost you any money.
right, it doesn't cost you anything. NYSERDA, and you can check out their website, and Southampton Town has a link to it. Right.
Right. However, I will say that you won't get an integrated approach. You'll get a laundry list of, you can do these different things, and they'll show you actually what the payback is in years, you know, or months or weeks or whatever it is. They'll show you that, and you can pick and choose. We find a lot of our colleagues approach this the way they approach the LEED checklist, for example. I accuse them of point trolling, because they're trying to get so many points to make the rating, gold, silver, platinum, whatever it is, and they pick the ones that is easiest, they cherry pick, easiest to achieve, without, again, really being concerned about the interaction of all these things, how they work symbiotically. And I don't know, I think you need, as Dieter is saying, I think you need somebody like us if you're interested in that symbiotic approach. I find that in the short run, it's the most cost-effective approach, and in the long run, it's clearly the most cost-effective approach. I'll also tell you that in Europe, where foundations go back to 1000 AD or earlier, the buildings, you would go as a tourist and there's a brand new modern bathroom there and so on, but the building is a very old building. They've been retrofitting constantly, and they're way ahead of us in terms of building performance. They exceed the 2015 IRC, International Residential Code standards, because they've been focused on and looking at these issues for decades and decades. So they know how to take old buildings and bring them up, bring the performance standards up. So we watch what they're doing there. We take the best technologies that are appropriate to reuse here, and we do that. But the integrated approach versus the point trolling is something that I think you need one person who has at least some kind of knowledge about all these things to help you come up with an overall plan, rather than just say, well, I think we'll do the lights this year, the windows next year, and, you know, in some haphazard way move through the building. No, those things, it would be a great idea, because right now, again, virtually the whole industry, I would say 99% of my people, well, let me start by saying this, a wonderful quote. You know, all these green and sustainable buildings and design, it's like high school people talking about sex, you know. Everybody talks about it, right? Very few have actually done it, and hardly anybody does it well. And it's what we find is the same thing here. I don't know how to engineer the kind of system, but the metric systems that are in effect now, the measurement point and certification systems that are in use now, all encourage the point trolling. They don't encourage symbiotic approach. You know? So if that's something that you could do, Tyler, it would be great. Just be great. Yeah. I think the closest center, the closest hub of those people would be Nessie in New England. There are very few people I know on Long Island. There are some, but I would say only 2 or 3 I can think of offhand. But New England has a very active center based around Springfield, Massachusetts, in New England Sustainable Energy Association. They changed their name. It was the Solar Energy Association when they started. So you could look them up and find if there's somebody willing to work here, just the way New York City architects work here, they would work here. Ed Mazur, yeah, again, in New York City there are some people, and the AIA, you know, has adopted that program, but I've had this horrible story that when the village of Shelter Island was looking to adopt one of these codes, the way that Southampton has adopted a more stringent energy code, they had a public hearing, and about this many people came to the public hearing, and I went to lobby for it, and 3 of my colleagues in the chapter of the AIA showed up to lobby against it. Even though the national position, the official position of the national AIA is in favor of all of this, you know. So, no, there's no other certification. They have a committee called COAT, CO, Committee on the Environment, But otherwise, you wind up like Ben and myself. We're certified lead professionals. And you can get that affixed to your name if you take the exam. You can take an exam and become a lead certified professional. And virtually everybody in the industry who is marketing themselves as being green and sustainable has done that.
Interesting.
You know.
Thank you.